Problems are not phrased in something like, given an array of n elements, pick the, sort the array or something. They're given in terms of real-world problems, real-world applications. Some of them are not so real-world, but they're phrased as such. And I have an example of this. This is a problem written by our very own Dan Pade here. This was on the advanced Code-a-Thon 3 semesters ago, I think. So I won't read the whole thing, but you can see Bobby Blue's a blue gremlin, so clearly we're, and then there's a joke in parentheses. I guess it's a joke. I think it's supposed to be one. But anyway, so the point is, so you have a blue gremlin, and then it gives you some information about the parentage, the family tree of gremlins in general and blue gremlins. And then it asks you to find the nth generation and sum up the n-1 and n-2 generation. So if you type this into Google, you're not going to get any results, right? This is a totally original problem. So what you have to do is you have to reduce it to a problem that makes sense computationally. The best way to do this, I think in a lot of cases, especially for problems like this where you sort of start small and then get bigger, is to work it out on pen and paper. Every time I've computed in a Code-a-Thon, I brought a clipboard and 20 or so sheets of paper and a pencil. And actually, I'd say I'm probably using that more than a computer for these Code-a-Thons. So really, you have to work these things out on pen and paper to really understand them. So let's actually work part of this one out. So has anyone read this yet all the way or understand it? Okay. So what it's saying is find the nth generation of his family. So obviously we're going to have to go up a tree to find that. So we start out with a blue gremlin. So I'm going to use the board here. I got to start low because we're going to go up. That's a terrible place to start. This is better. If someone can't see, let me know. I'll try and do something. Huh? Oh, that's a good idea. Left to right. All right. We start out with one blue gremlin. So this is at the first generation, n equals 1. All right, and one red parent. So draw a line and draw an arm. All right. So now at this generation, generation 2, we have one red gremlin, which have two parents, a blue and a green. So we're going to just draw this out, blue and a green. Third generation, blue gremlins have one red parent. Greens have 3 parents. 2 blue and another green. All right, we'll go a couple more. Red has a blue and a green. Blue has a red. Blue has a red. Green has 2 blues and another green. Blue, blue, green. All right, we'll do one more. I think maybe is enough. All right. Reds have blue and green. Blues have red. Blues have red, and greens have 2 blues and a green. All right. So this is our family tree for 6 generations, and now I'm going to go ahead and tally up how many we have in each generation. That's not an N. I don't know what that is. All right. So at generation 1, we have 1 blue gremlin. Generation 2, we have 1 gremlin. Generation 3, we have 2. Generation 4, we have 4. Generation 5, we have 7. Generation 6, we have 13, I think. Yeah, 13. All right. Does anyone see a pattern besides Dan? What's the pattern?
Each one is a sum of the 2 preceding.
You're close. So 7 plus 4 is 11 here.
No, I mean, it's 7 equals 4 plus 2 plus 1. That was the 3 preceding.
Oh, the 3 preceding, exactly. All right. So what does this look like? But not quite. Fibonacci, all right? This is close to Fibonacci, but it's not quite. So we can generalize this to say the number of gremlins we have at the nth generation, so I'm going to do this f sub n, is equal to f sub n minus 1 plus f sub n minus 2 plus f sub n minus 3. All right? So already, this makes so much more sense. It's so much easier to reason about as a computer scientist than this 3 paragraphs of gremlin parent tree code or discussion, right? So, and then it specifically asks to find f of n for some n, and then to sum up f of n minus 1 and f of n minus 2. So I should note for our Code-a-Thons, the format is 24 hours. I think we're probably going to stick to that. We may change it to 12. It is to be determined. But it's 24 hours. You're going to have 6 to 8 problems. So you have multiple hours per problem, 4-ish potential hours. You're not necessarily expected to stay awake the whole time, but if you do, you'll probably do better. So if you have 4 hours for a problem, this is pretty much the whole problem description. So this is expected to take you 4+ hours. This was actually the hardest problem, I believe, of that one, so it should take more time than the average. So this right here actually doesn't seem like that hard of a problem. Turns out it is. But reducing the problem into something that you can understand, and also for our Code-a-Thons, you can and are encouraged to use Google. Our Code-a-Thons are more about learning than showing what you already know. So being able to Google these things and figure out the answer pretty much however you want is fine, just as long as you don't blatantly copy code. But this is a much easier problem to handle than that one. So reducing the problem into something that can be understood is incredibly important for being able to solve these problems. All right, so step 3, after you reduce your problem, is to determine the type of problem. And there's lots of different sort of categories that you can group problems into. For the purpose of this presentation, I grouped them into sort of 2 overarching ones, which may sound confusing at first. Data structure problems and algorithm problems. So the concept of a data structure doesn't really make sense without algorithms associated with it. So that's why data structure problems really are algorithm problems, just masked with lots of data. But knowing the difference between what you think an algorithm problem and a data structure problem might be will really help you in finding out how to solve the problem. So data structure problems usually, not always, but usually have some sort of question like, given n elements of something, perform a query on these elements k times. And an algorithm problem usually has a very small input and saying, find the output given this input. So you have one function that takes one input and finds the output. So for example, this problem right here, the input is one number, I believe. It is just n. And you are supposed to find f of n and sum up f of n minus 1 and f of n minus 2. So what kind of problem do y'all think that this is? Throw it out. Well, yes, but specifically it's an algorithm problem, right? A data structure probably isn't going to help you a whole lot here because you don't really need to keep track of lots and lots of things. As opposed to a problem, not like that one, like this one. This is a data structure problem. And you can see, so you have a list of n trees, and later on you need to find k different height sums. Okay? Yes?
What if you made a tree, and then based on each of the nodes you could branch out, and then you could start doing like infinite sums based on the tree?
So you can approach this as a data structure problem, like you said, and do a tree. And if you implement it, you will find out it is way too slow.
Okay.
Yeah, this is, at a later date, we may go over how to actually do this problem completely. It ends up you have to use matrices and then do exponentiation by, I can't remember the word, but you have to, yeah, exponentiation by squaring. Yes? You have a question?
Are you done?
Sure.
I was going to say maybe you should talk about time constraints.
Oh yeah, that's coming up.
Okay.
Yeah. So this is a data structure problem because we have k queries on a list of in this case, numbers. So we need to be able to optimize the query time. That's kind of an important step here. And I may talk about the solution of this problem in a bit as well. All right, this problem. just looking at it real quick, is it more likely to be an algorithm problem or a data structure problem?
Data structure.
Yes, data structure. Again, both of these last two problems were written by me, and I actually use exactly in and k to try and give a hint. So the way you solve this problem is with a certain type of data structure. All right. So in general, to solve data structure problems, there's a time-old phrase that goes along with these that is keep the array sorted. So if I give you, like, how many people are in 145? Okay, have y'all gotten to arrays yet? All right, so for this purpose, it's a list of numbers, right? Or a list of anything, but we'll say a list of numbers for our purpose. So if I give you a sorted list of numbers and say, what is the biggest number in that list? How fast can you tell me? It's instant. It's the last number in the list, right? It's instant. If I give you an unsorted list, how fast can you tell me what the largest element is? You have to look, not in or two, in.
Average.
It's in, always.
You have to compare all.
Best case and worst
You only
case.
have to go through once and keep track.
Yeah, because you have to look at every single element in the array and keep track of the maximum element and go through every single one and look. So if I say, given an array, and we're going to change the array throughout the course of the problem, and I always want you to find the maximum element, if every time I ask you to find the max, you scan through the entire array to pull out the max, that's going to be way too slow. All right? So data structures allow us to make assumptions about the data that we have that lets us perform extremely fast algorithms on them, especially in certain cases. So if you're kind of lost, you don't know what to do, and you know it's a data structure problem, think about the phrase, keep the array sorted. Think about how you can sort your data and keep it sorted so that you can perform the query that you need very quickly. All right, algorithm problems. So for our Code-a-Thons, these are actually usually kind of really, really hard. Dan writes a lot of them, and he's like PhD, did physics undergrad, you know, all this fancy stuff. So he writes hard problems. So you're not going to know how to solve them. All right, you're going to need to use Google, and this is okay for our Code-a-Thon. Again, the point of these is to learn how to do them. So like I mentioned earlier, the exponentiation by squaring for matrices, this is something that I could reproduce relatively quickly, whereas it took me 4+ hours to do it the first time. So know how to Google, be able to reduce your problem to something that can be Googled. Again, if you have something like this and you search efficient ways to compute Fibonacci, that's a great Google search to get you started on finding fast algorithms on how to compute this exactly. Whereas if you searched Gremlins Gone Wild, exploding parentage, I don't know what you'd find, but it would not be coding advice. All right, so now consider your restraints. So before and I'll mention the next slide as well, is consider your asymptotic goal. So we need to talk real briefly about what asymptotic goal means, because I don't think you get to this until 146, maybe, somewhere around 146. And if you were here last week for Dan's quantum computing talk, you heard him talk about algorithmic complexity or asymptotic complexity or notation. And you'll probably hear about it at most of the talks for the rest of the semester and next semester. If you haven't guessed, this is an incredibly important topic in computer science, and specifically algorithms. A lot of you may not like it when you first hear about it. It's kind of confusing at first. I didn't like it. I use it all the time now. You can't escape it, so go ahead and embrace it. But I'll talk about it real quick. So basically, it means what is the growth rate of an algorithm. So as you increase the input, how much extra time does it take to produce the correct output? So if I ask you to sort a one-element list, this is very easy. You're done. There's nothing to sort. If I ask you to sort a two-element list, you need to make one comparison. Check which one's bigger and swap them if the one on the left is bigger. A three-element list, you need to compare more elements, and this grows. And we say it grows at a rate of n log n, which I won't talk about what that means exactly, but basically you want to get this number, your asymptotic goal, as low as possible in terms of n. So I'll start out talking about just in. So this is linear. So for example, if you have an array, you need to find the max of the array and it's not sorted. There is no way to do this without looking at every single element of the array. If the array has in elements, it means you have to look at in elements. So we say that this algorithm runs in linear time, or with respect to in, we say it runs, well, with in. All right? This is less than in log n. So if you haven't done a whole lot with logarithms, you will get to that when you start talking about asymptotic notation. But log n, if n is a positive number, this is a positive number, times n is always going to be larger than n. All right, and then as we keep going up, you get to n squared, n cubed, so on and so forth, and then really big numbers like 2 to the n. If you ever hear, well, I'll talk about the other side first. So then on this side, let's see, square root of n is better, which is not as good as constant time. So what I talked about earlier, if you have a sorted array of n elements, and I ask you to find the largest one, this is a constant time algorithm because you have to do one operation. It doesn't matter how many elements are in your sorted array. It takes the same amount of time, so that's constant time. All right, and if you look at this and kind of remember this, this will actually help you a lot for 350. This is a test question on 350 exams. But basically, if you are doing some Googling, looking for an efficient algorithm, you want to find one that is as low on the chain as possible because then your code will run faster. Very often, the lower ones are going to be harder to implement. There are some simple problems like sorting, for example. Some of you may have heard of bubble sort. Bubble sort runs in n squared time, which is not very good for sorting. Most comparison-based sorts that are used today, like quicksort, merge sort, tensor sort, etc., run in n log n time. There are some super special sorts that work on very specific types of data, like radix sort, which actually run in linear time, but those are not very commonly used. But also, if you ever hear someone talk about an easy problem in computer science versus a hard problem, this is easy. And anything greater than that is hard. Kind of as a simple way to think about it. But this is a super fast crash course on algorithmic notation or asymptotic complexity. You will learn more about it, so don't worry. You're going to have to learn it if you want to succeed as a computer scientist at this university. So, consider your restraints. All right. If I say I need you to perform 10 queries on an array with 100 elements max, and let's say this query is to pull out the largest element, and your code needs to run in under 10 seconds, you don't have to sort the array. You can just go through every time and find the max, and it'll be plenty fast enough. If I say, given an array with 1 billion elements, and you need to perform 1 million queries on the maximum element, well, you probably can't do that. It's probably too slow, right? So this value of n, and we almost always use the number n. So you can see here, you're given a list of n words. Here, you have a list of n trees. So if you see n, that's probably a decent idea to use for this. And I don't have a screenshot, but all of the problems that we write, and I think most Code-a-Thons in general do this, they give you constraints. So they say, we promise on any of the test cases that we give you, n will not be greater than, actually there is, right here. So you're promised n is no greater than 1 e to 15, right? This is a huge number. This is an extremely large number. So right there, you can look at that and you don't have to worry about making this whole tree because you know there's no way it's going to be fast enough, right? And you start to learn these things through intuition and practice. But if you just look at this problem without this promise here and without the constraints, what you may try and do and what I've tried to do is literally just write a super simple formula to compute Fibonacci. Just do it recursively. It worked for all but the last 2 test cases, and then it timed out. All right, and then after like 3.5 hours of work, figured out a different method that ran in 9 milliseconds on every single test case, even the really, really big ones. So this algorithm was way lower on the chain than our original one, which would have been, I guess, around linear time.
You found a constant solution to this problem?
Oh, no, not constant. Just much faster than hard coding, yeah. there's a trick you can do with Fibonacci where you use a matrix and multiply it a bunch of times, and then there's tricks to optimize that. But yeah, so consider your constraints, because if they're small, you may be able to get away with a not quite as elegant solution that you can probably pump out a lot faster and a lot more easily. All right. Now consider your asymptotic goal. So if you're looking at a problem and you think, okay, I think there might be a way to do this in n squared, okay? That means that you can sort for free. And what I mean by that is sorting for any sort that you're going to use. So Java's arrays.sort, Python's built-in sort method, they all run in n log n time, all of them. So if you're saying, I think I can do this problem in n squared, but it would probably make it easier for me to solve the problem if the array was already sorted, just sort it. All right? You don't have to worry because n squared is much larger than n log n. So you can do the n log n without worrying about it killing the time that it takes. If you think, okay, my constraint is really big, so I probably need to do this in linear time or faster, then you don't have time to sort. Right? Sorting might take too long just by itself. But if you can sort, if you think it's going to be bigger, I highly recommend it. There's really no downside, it doesn't take much time, and it will probably make your life a lot easier. Alright, another very important step, persist. So, all of the Code-a-Thons that we've had so far, the winners have worked on them for 17 plus hours out of the 24. Alright, this is a long time, I know it's tough, but you're competing with people who are willing to do that, and you also have to be willing to do that if you want to win. If you just want to have a good time and learn, then it's fine. But you have 24 hours to do this. It's a long time, and you should use it. I think pretty much everyone takes a nap somewhere in that time. It's not expected that you're going to work for 24 hours straight, but in every one that I've competed in so far, when I left Swearingen, it was light out. So be sure to persist. A lot of Code-a-Thons, like the one that we go to at College of Charleston, ICPC, it's 6 hours because they're not.
No, it's 5.
5? It's 5 hours. 4? Okay, it's 6 or fewer. Right? Upper bound is 6 hours. So this is not as hard, right? I think everyone in here can sit down and code for 6 hours straight. If you get it, you're going to be doing that anyway, so get used to it. But you do have 24 hours, it's a long time, and the more time you spend on it, the higher your score is going to be, the more you're going to learn, and the better you're going to do. Alright, so now I'm going to talk about some general tips. These are, actually I didn't talk about technical interview stuff at all, so I'll go back real quick and do that. So read the problem. For technical interviews, well, for the ones I've done, I haven't gotten a sheet of paper, they've been spoken. But make sure you understand and ask questions. Questions are good, it means you're listening. Reduce the problem. You still want to do this step, absolutely, but do it out loud. Every time you think of something, just say it. Right? That's what they're looking for. They're looking for your thought process as you go along and do it. And then determine the type of problem. Again, you can do that out loud. You can say, well, I see that I have to do repeated queries, so it would probably be good to use some kind of data structure here. And this also gives you more time to think of what data structure you might want to use. And also make sure if they don't give you restraints, ask for them, because this will affect your answer potentially, and it will show you that you sort of know what you're talking about. And this as well, you should ask or think about, well, I think I can do this in n squared, so I know I can sort at the beginning for free. Or you can say, I think this needs to be done in linear time, so maybe I should approach it from a different way. And this shows that you at least have the intuition, even if you don't have the answer. So this is a really good way to sort of impress someone, especially if you don't actually know how to solve the problem outright. Alright, so for our Code-a-Thons, we allow a huge variety of languages, from the usuals, Python, C, C++, Java, to some kind of weird ones like SQL, which I don't understand how that. Also Bash. I know Clay's tried some in Bash.
It's real slow.
It's real slow. Not recommended. Each language has a different amount of time for our Code-a-Thons that it allows you to do. So for example, if you write your code in C, it has to finish in a second. If you write your code in Python, you are given 10 seconds.
Or this won't work.
Or yeah, write your code in Java, I think it's 4-ish seconds. C# is 4-ish seconds.
Depends on the problem.
Yeah, it depends on the problem, because for some problems we have really big inputs, so we make the time longer. So you have to, yeah, so we have a huge variety of languages, which means you can choose the one that you like. Even at ICPC, we had choices of C, C++, Python,
Fortran.
Java, yeah, Fortran, as and I think they also had like Haskell and a few other ones.
Haskell.
The national one was only C++, C, and Java, I think. But you all know Java, or you should know Java to some extent, and C is an invaluable tool to learn. I highly recommend it. But whatever language you choose, you should know the standard library. So there are tons of built-in functions in most languages. C has a lot of like stuff you can import to give you some power. So you know, there's no point in writing your own merge sort function, right? Use arrays.sort. It's going to be much faster than anything you can write because it has literal years of optimization behind it, and more importantly, it saves your time because you don't have to worry about writing your own algorithm. For every Code-a-Thon that I participate in, I use Python because the standard library is incredibly powerful. Okay, we have lots of problems, or we have had problems in the past where it involves dealing with numbers on a binary level. And in Python, if you have a number, let's say x equals 11, that's a bad example because that just uses ones, say 72, then you can just write bin x, and you get the binary representation of 72, just like that. Let's say you have an ASCII character like A, right? And you want to convert this to the ASCII code. There's a way to do this in Python. You can write like a lookup table and whatever, or you can just do ord A, and it'll spit out the ASCII representation.
You can also do int A, I'm pretty sure. Actually, that might give
Maybe,
it.
yeah.
That might just give like the number of
Yeah.
the alphabet.
Yeah, I'm not sure how a lot of them work, or like down the level, but I know this one will give you the ASCII code numeric for that. The sort function obviously will sort a list for you. Another thing about languages is you should know, for specific algorithm problems, you should know how they implement their data structures, because it's different in different languages. I think in Python, lists are linked lists by default, I want to say. So linked lists work differently than base arrays. And so you should be aware of these differences if you want to really optimize your code. And for some of the harder ones, the advanced categories, for like 240 and 350 ones, you're going to need every optimization that you can get. So it's really helpful to know your language's standard library. I mostly know Python, so I can't really speak for other languages, but the PyDocs online, you can click standard library documentation, and they have documentation for like around the first 6 modules, or where all the really useful stuff is. It doesn't take too long to read. I know it sounds dull, but it will make you a much better Python programmer if you can do it, or for any language that you choose. All right. So have your own standard library. So I'm not talking about functions that you've just memorized, although I guess that's kind of what memorizing an algorithm is. But programmers kind of have some tools in their toolkit that they can pull out to solve certain types of problems. So who here has heard of binary search? All right. So binary search is incredibly useful. All right. Basically, what it means is if you have an array of in elements that's sorted, you can perform binary search on that array, and you can pick out the element you want in log in time, which I didn't put it up here, but that is right here. Or it's right here. It's right here, right? Log in is right here. This is in to the one. Yeah.
Below,
Alright, so this is much faster than doing something linearly, right? So if I say, alright, pick out a given element in an array, you have to do this 100,000 times. If you can do it log in, that is way faster than scanning through the whole array, right? So binary search, there are certain data types or data structures like binary search trees you might have heard of. But binary search is much more useful than just in the context of binary search trees. And this is something that you should sort of have in the back of your mind on ways to apply to problems. I had some other examples of useful things.
reverse in Python.
Well, yeah, that's part of the standard library stuff, though. But there's other general tools and algorithms that you can sort of learn over time that can apply to a wide variety of problems. All right, so know how to debug your code. If you run your code, you get incorrect output. You can poke around in the code and try and get the correct output for a long time. Or what I recommend is try and find out where it goes wrong so you can figure out what you need to fix. So in HackerRank, which is the platform we use for our Code-a-Thons here, you can put print statements in your code, print out anything you want, and it will show it in the console after your code executes. So if you are trying to sort an array and perform some operations on the array and you're getting the wrong code, well, print out the array. Make sure it's sorted before you go on to the next step, right? And you can put these print statements everywhere. You can't leave them in the final version of your code when you submit it. Your code will be marked wrong because it will see that as output and it's not smart enough to figure out that that's debugging output. But I think every single programming language under the sun is going to have some form of print statement. And you should at least know how to use that for debugging, if not more powerful tools. If you're writing locally, like on your own computer, you can use more powerful debuggers that let you step through the code, do all sorts of cool stuff. But personally, I've never done that, and it's been okay. So print statement debugging is pretty good for these Code-a-Thons. All right. Now this is a slightly rhetorical question for all of you. I want people to try and answer. So what's the best way to get the answer for a hard problem? Any ideas at all?
Ask Dan.
What?
Ask Dan.
That is a good way. Actually, he's probably got the answer, but for Code-a-Thons, unfortunately, we can't do that. Anyone else? Anyone have any ideas?
Use your brain.
Use your brain? Well, that's got to do that.
Yahoo search.
Huh?
Ask Jeeves.
Yahoo search,
Dog
Ask
pile.
Jeeves. I wouldn't recommend either one of those, but you're close. All right.
Take a nap.
Taking it. Well, that helps sometimes.
Assign it to a lazy person. They'll find the cheatiest way to do it.
Yeah, if you can, you know.
Can you split into smaller problems? Well, split into smaller problems.
That is a real answer. That's actually good. Yeah, this is a general purpose technique. If you can split your problem into smaller problems and solve those, that's good. But this is actually a trick question. The best way to get the answer to a hard problem is to already know the answer. All right? And you can do this by practicing, right? So if you do Code-a-Thons on your own, I know this may sound boring, but it's really not that boring. Kind of fun. I do it all the time. But if you practice a lot, you can run into problems, and then when you see the problems on the Code-a-Thon, you already know the answer. All right? And so I'm not going to just leave you with that. I have some resources. Those are tiny. Can I zoom in? How do I? Well, I'll just say this. All right. So there's a thing that people do called Code-Kata. I think it's a really dumb name. Kata comes from like karate. I don't like. It's coding, a martial art. I don't like it. But anyway, they're called Code-Kata. This is something you can Google. You can find little digestible coding problems to practice on. Some resources that I recommend. If you like math, does anyone in here like math? Awesome. All right, math is awesome. Math is great. So if you like math and you want programming questions oriented on the math side, projecteuler.net has a huge list, like 480 something problems in increasing difficulty that are all essentially math problems, but are too complex to solve by hand. And I think Project Euler number like 16 or 18, actually I stole and put on a Code-a-Thon last semester. I changed it, but this is, if you had done that problem, then you would have been able to figure out the Code-a-Thon problem pretty easily. So, you know, practice. If you do these, they will help you on the Code-a-Thon, I promise. All right, hackerrank.com, this is the platform we use for our Code-a-Thons. So if you're interested in participating in the Code-a-Thon, even if you don't want to do a lot of practice, I recommend doing the basic HackerRank problems just so that you can familiarize yourself with how HackerRank works. So you need to be able to know how to get input from standard in, how to print the standard out, how to do some basic operations. HackerRank actually has an IDE on the website, which is kind of shitty, but I've always used it, and it's fine. I don't know, like it's not good at all, but if you use their IDE, you don't have to worry about running the wrong version of Python on your local machine or having a different C compiler that causes problems. Not that I'm saying you should do that. If you are more comfortable in a local editing environment, by all means do that, because it will probably be faster and better for you. But I recommend spending like an hour playing around with HackerRank. They have some really easy problems like in Python, add 2 numbers, that kind of stuff, just to get yourself familiarized. And if you are inspired, you can keep going, and they actually get really difficult problems. HackerRank routinely runs actual competitions, like University Code Sprint, I think happened last weekend, and other things that you can compete in, and potentially win money or jobs or a shirt.
Can you post a slide to the Facebook page?
Yes, cool. Absolutely. Yeah, or a shirt. A couple of us actually got shirts from a HackerRank thing a few years ago, which is kind of neat. It's just a shirt, but it's kind of neat. Codewars.com. So I should mention Project Euler. You put in the answer, right? So you don't submit code, you just submit the answer. So you can do any programming language you like, or even work it out by hand. Some of the earlier problems you actually can work out by hand, but I don't really see the point. Yes?
Oh, yeah, I just want to say, like, every pre-coding test I've ever had to do for a job interview has been on HackerRank.
Yeah.
So
it is.
like,
You might as well learn it because you're going to probably have to use it at some point anyway. So HackerRank and Code Wars, you put your code out there and it runs your code for you. Yeah.
Actually, Code Wars is cool because you can log in as University of South Carolina. And currently right now, I think it goes Jeremy, Tori, me. And there's no reason why I should be in 3rd place. So we need to get more people on there like actually.
Yeah. So what he was saying, Code Wars, like you join like a clan or something. It does this Code-Kata karate bullcrap.
I think it's sick.
If you like it, great. If you don't, ignore it. Which is what I do.
Don't you get on there?
But
Yeah, please beat me.
join the
I should not be
University of
second.
South Carolina clan. They rank, like, as you solve problems, they have difficulties, which is ranked in, like, Q or something,
It's really cool because it scales very, well. As the problems get hard, you start at, Kata 10 or something like that.
Yeah.
And then those ones are pretty simple. They might be, like a 145 was the last question. And you're going along, you feel really good about yourself. It's kind of hard, but Corey's really close. So if I spend 2 more hours before my Adderall wears off, I might be.
We do not condone that, by the way. We're recording this, so.
They can't hear me over here. I also have a prescription.
Yeah.
It's really fun to actually compete against people you know. That's actually my
it is a lot of fun, and I haven't done one in a while because no one's competing. So
I'll get on there.
yeah, get on there and let's make this a competition. Let's make it fun. Geeks4geeks.org is the last one I have up here. It's not problems like the other ones, but it has incredible explanations. This is something I started using recently. Incredible explanations. I'm more than happy. I'll sit down with you. We can walk through it together. All right? Seriously, use me as a resource or any of the other leaders in ACM. We're very happy to help. We want to see all of you succeed and do well. So yes, use us, please, as a resource. Also, there are some other resources, so I have a link here. This is to MIT OpenCourseWare. How many people have heard of OpenCourseWare or something similar? Oh, okay, most of you, great. So, lots of schools, MIT, Stanford, have started publishing their lectures online for free to watch in video format. There's also Coursera, Udemy, I'm missing some, but there's a ton of these programs, right? And some of them even have testing quizzes that are graded for you, all automated, but it works. This is super useful, all right? You will learn so much, and I mean like a ton. If you go through this course and do the whole thing, it's intermediate for MIT, so it's kind of advanced. But if you go through it and do the whole thing, you will learn a tremendous amount about computer science, okay? My freshman year, I did a Stanford online course. I did the intro to algorithms course over there. I did not do super well in it, partially because I stopped watching the lectures halfway through. But even that much helped me an incredible amount, right? If you watch these lectures for an hour, 2 hours a week, it's going to help you a lot, and it's going to help you in your future classes here as well. I think this is my last slide. Any questions at all? Okay. Well, it's it's the internet. All right, not bad. So thank you all for coming out. I will post at least this slide. I don't think the other slides are useful, but I'll post this slide on the Facebook page. Highly recommend you check out these resources, especially HackerRank, and I look forward to seeing all of you at the Code-a-Thon sometime next month.
Yeah, so I was gonna say, I think we're planning on having the Code-a-Thon in the end of October.
Or the beginning.
Or the beginning, which is pretty soon, so I don't know about that. But probably at the end of October.
Don't be super intimidated by it either. Like, you can come for a couple hours, sleep the night, wake up and still
No,
do some work.
I realized I probably put a lot of pressure.
It's not that.
low
It's like
pressure,
very
right?
enjoyable.
Come and hang out.
We've got
we
food.
have pizza, we got food.
Yeah. Probably catered food, not
Well,
I have to.
Yeah, I worked on it for like 2 hours when I wasn't even a CS student and got second place because
I almost thought
somebody was already a degree. But yeah, thank you for coming.
Would you be anyone else?
Yeah.